I want to first introduce our principal mentor this summer, Sewon New. Sewon, welcome, and the floor is yours.
Thank you for the introduction. Maybe I can share my screen. Great. Hello, everyone. Welcome to the QED-C Summer Internship Final Presentation. My name is Xu Yuan. I'm an assistant professor from University of Central Florida. This summer, I'm very happy to be the mentor with Tom for this internship program. First, let me introduce our three amazing interns this summer. They are Nir from University of Central Florida, Anish from UIUC, and Hrushkesh from NC State University. Before we start the presentation, I want to acknowledge all the collaborators. We have collaborators from Unitary Foundation, including Vincent, Alexandro, Chenghao, and Nathan, and also collaborators from Sandia National Lab, including Tim and Noah. We also want to thank the valuable suggestions given by Sonica and Avamida. This is the agenda of the presentation. First, the interns will present in the order from Nir to Anish and then to Hrishikesh, and Q&A session will be at the end of the presentation. So now I will stop sharing, and Nir, the floor is yours.
Yes, thank you. I'll share my screen. All right, and can you guys see my screen? Thank you. Hello, I'm Nir Patel, and I'm going to be sharing QED-C's collaborations in quantum benchmarking this summer. To give you an overview of today's presentation, I'm going to talk about QED-C's architecture and integration challenges, as well as the collaborations like Sandia National Laboratories and with Unitary Foundation. To give you some insight into the current QED-C structure so that you can understand the integration challenges better, the structure right now is that each benchmark, for example, quantum Fourier transform, Hamiltonian simulation, and so forth, has subdirectories with APIs. By APIs, I'm referring to Qiskit, Braket, Cirq, and CUDA-Quantum. Now, within each API subdirectory, there is a benchmark file that users can run. To run a benchmark, you run it as a sweep of qubits and circuits. So for min qubits being 2 to max qubits being 6, and to skip qubits of 1, you would generate a sweep of qubit sizes 2, 3, 4, 5, 6, with a certain number of maximum circuits within them and a number of shots to execute each circuit's with. The new architecture we have, and we've been developing, is that each API subfolder now has API-dependent code only. This consists of things like circuit creation and circuit drawing. And there is one top-level benchmark.py file where all the execution of the benchmark and analyzing the results is handled. This new architecture gives us a more modularized approach, which benefits our integrations. Even with this new architecture, there are still some challenges that we had within integration. First and foremost is that the framework only supports end-to-end execution, meaning that users and other users cannot access the problem generation, analysis, and execution portions independently. Further, there's reliance on file path manipulation for dynamic kernel imports. What this means is, say we want to run our benchmark with Qiskit, we need to import the respective API file for it. Now, instead of Qiskit, if we wanted to run it with Cirq, we would need to import the Cirq kernel file. To address the first issue, what we've done is we've added a get circuits flag. What this does is it suppresses execution and returns circuits and circuit metrics, like create time. This prevents that end-to-end execution and gives users more flexibility and freedom to customize circuits and what they do with it, like how they execute them. But this does not fully address those integration challenges. So what we've done afterwards and continued developing is a QED-C packaging using Python's setup tools and import lib packages. So the steps to use the new package are you would clone the repository, navigate inside of it, and run pip install. The benefits is that you can use the QED-C suite as a submodule, and it gives modularized access to functions and variables. For example, some functions would be like the polarization fidelity computations, and some variables would be the circuits themselves for each benchmark. Some collaborations that have utilized our new architecture are with Sandia National Laboratories and their Pigsty framework, and Unitary Foundation with their metric GIM framework. To jump into Pigsty, Pigsty is an open source Python implementation of gate-set tomography, and it's used for modeling and characterizing noisy quantum information processors. An example, systems of one or more qubits. Some motivation behind this integration is to leverage the QED-C algorithmic benchmarks and study them in noisy environments. Things with like crosstalk errors, coherent errors, and time varying errors. And the main thing is that these simulations are reproducible, so we can customize them as we please and reproduce the results to see how certain hardwares work with these algorithms. The steps for this integration include, first, within Pigsty, we choose which benchmark we wish to run. Then QED-C will create the circuits and return the circuits to Pigsty, where Pigsty will then map them to Qiskit simulation devices, convert the circuits to Pigsty, define a custom noise model, such as crosstalk, coherent, or time-varying errors, then execute those circuits, and QED-C will use its analysis methods to compute the fidelities. Pigsty will then plot the results and give it back to the user to analyze and see the effects. An example of this integration was with our quantum Fourier transform. And these are the results that were produced, where on the x-axis, we have the number of qubits that were swept over. And then on the fidelity axis, or sorry, on the y-axis, we have the fidelity, the average fidelity of the sweep. And we can see that we used crosstalk errors and no crosstalk errors. The next collaboration was with Unitary Foundation and their metric software. Metric has a mission of community-driven quantum benchmarks, where users get to submit their own benchmark results. So on this plot, you can see that users have submitted on numerous devices with numerous providers over the span of a couple of years. And you can see the metric that was used here. Quantum volume is one of the benchmarks in metric GIM. Now, you might be wondering, how do users submit and run benchmarks? It's done through their metric GIM framework, which is what lets them run quantum benchmarks on different quantum devices, such as IBM, IonQ, Broquette, and some of the others that were listed in this plot, Quantinuum, Rigetti, and so forth. Now, the motivation behind integration with Unitary Foundation is we want to add some application-oriented benchmarks to their suite. Additionally, metric GIM allows users to dispatch and pull benchmarks separately. What I mean by dispatch is users can create and send the benchmark to quantum hardware, and that will end the process there. Then it will run, install, and wait on their code to finish there. Then eventually at a later time, users can pull, which will ask the cloud to return the results. This usability gives users more freedom and doesn't waste their time on their system. Additionally, we can run benchmarks on new quantum hardware, such as IQM and many of the others that aren't currently available through QED-C's suite. And lastly, there's the community-driven publishing of QED-C benchmarks onto metric info. To walk you through the steps of the integration and how the process runs, let's start with dispatching first. Within metric GIM, you would define a JSON file with the arguments for the benchmark. Note that we have number of shots, min qubits, skip qubits, and so forth that are very similar to how the current QED-C suite runs, the new one being the benchmark name that gets specified. Then metric GIM will validate the schema, ask QED-C to get the circuits and circuit metrics. Then it will dispatch to quantum hardware of choice through metric GIM, store the job ID, and then terminate the process there. So the user doesn't have to sit and wait for the cloud to finish computing it. Then at any other later time, the user can select a job ID to pull. And this is what the interface currently looks like, where you have the metric GIM job ID, the index that you wish to pull, the provider, device, what benchmark it was, and the time of dispatch. Then the user chooses then metric gym will go to the hardware and try to pull the results. It will check whether the job has finished. Let's assume the job has. Then it will obtain the counts, ask QED-C to compute the fidelities and create any plots. Then the user can choose to publish on metric info and it terminates. Otherwise, if the job hasn't finished, then it will inform the user to try to pull this job at a later time, and then it will finish. Here's an example of our unitary foundation integration results. Here you can see on the left where we have a volumetric plot. Note the circuit depth and the circuit width being the number of qubits, and the fidelity coding over here, where the plots from QED-C and the plots from metric gym look very similar. These were ran on IBM Fez on August 8th, and this highlights that the integration was successful, where running benchmarks through QED-C and through metric gym reproduce the same results. So in conclusion, we've improved the architecture for flexible integration, and we've demonstrated these integrations with Pigsty and metric gym. In the future, we wish to add more complicated benchmarks like Hamiltonian simulation and variational quantum algorithms. The current benchmarks that have been integrated are quantum Fourier transform, phase estimation, hidden shift, and Bernstein-Vazirani. We chose these four so that we can focus on the integration itself over the intricacies of the benchmarks. Additionally, we want to analyze more benchmarks through Pigsty, such as amplitude estimation, and we want to use our benchmarks in some of the other more interesting applications within Pigsty. And we are open to new integration with other quantum benchmarking frameworks. Thank you. And I would like to hand it over to Anish to talk about dynamic circuits.
Thanks, Neil. I'm Anish Giri, and I'm going to present my work on benchmarking dynamic circuits. The motivation of the research. We wanted to explore dynamic circuit implementations and their execution. We also wanted to explore the challenges and constraints to implement them and report any advantages of such circuits. And this would be a new addition to the existing QED-C benchmark. The topics covered. First, I will introduce you to dynamic circuits, quantum Fourier transform, QFT, and quantum phase estimation, QPE. Then I'm going to talk about the existing QFT and QPE benchmarking methods, and QFT and QPE benchmarking methods with dynamic circuits. And finally, I'm going to talk about the results and conclusions. Dynamic circuits. It's a circuit that has mid-circuit measurement with real-time feed-forward mechanism. It is based on principle of deferred measurement that states that delayed measurement do not change the probability distribution of the outcome. Here is a simple demonstration of a dynamic circuit. The figure on the left is a static circuit for a 2-qubit system. It has Hadamard on the first qubit and a 2-qubit rotation gate. Finally, we perform measurement. So for this static circuit, the dynamic circuit variant would look like this. You apply Hadamard, and as soon as you apply the Hadamard, you measure the first qubit, and based on the outcome, you apply a single qubit rotation gate on the second qubit, and you finally measure the second qubit. This would allow you to reuse qubits, and it will also allow you to save resources. This also creates possibility of adaptive algorithms. For this research, we wanted to explore simple variants of these algorithms, and we chose QFT and QPE. Quantum Fourier transform, QFT. It is quantum equivalent of a classical discrete Fourier transform. What it does is it converts computational basis states into phase-encoded superpositions. Here is a simple circuit diagram for a QFT 3-qubit system. You apply Hadamard, and you apply these controlled rotation gates, where the first qubit is the control, and rest of the qubits are the target. And this pattern holds same for the rest of the qubits. These dots represent a scalable circuit design with this single and 2-qubit rotation gates. And you finally measure all these qubits. The dynamic quantum Fourier transform variant would look like this. So instead of applying instead of applying this 2-qubit rotation gates, you apply this control single qubit gates, based on the results or the outcome that you get from the measurements right after this Hadamard application. So you apply Hadamard, you measure the first qubit, and based on the outcome, you apply all these rotation gates, and the phases of these gates scaled by the factor of 1 over 2 power k, where k is the index of the qubit. As you can see, the pattern is quite nice. That there are also some like long connections between the first qubit and last qubits, and if we can somehow measure the qubits in the beginning, and we can use the information to apply these rotation gates, then the idea is maybe there is some improved fidelity. Quantum phase estimation, QPE. It estimates the eigenphase of a unitary operation. What it does is it maps the phase information into an ancillary register with all these controlled unitary rotations. The circuit diagram looks at this. You prepare the quantum circuit with its equal superposition with all the Hadamards, and you apply these controlled unitaries, and you finally apply an inverse quantum Fourier transform. And you finally measure the ancillas to extract the phase information. So that was the introductory ideas about the research we are doing. Now, the goal of this research was to implement dynamic circuits in the existing QFT and QPE benchmark and compare the performance metrics. We also wanted to examine dynamic decoupling effects on these dynamic and static circuits. Dynamic decoupling. What it does is it applies a sequence of time control pulses to the qubits, so it cancels out environmental noises by refocusing qubits. And the goal is to keep these qubits engaged while it gets unaffected by all these environmental noises. Some of the common sequences are XX and XY4. The picture you see on the right is a XX sequence, and this XX sequence is sandwiched between these delays. And you can apply these common sequences in between the existing logic gates. So for the QFT benchmark, we already had two existing methods in the QED-C repository. The first method, it prepares the initial state with a bit string S, and then it applies QFT, and then it applies a bunch of single qubit rotation gates. And finally, originally, it applied static inverse quantum Fourier transformation, and you finally measure the qubits to recover or to extract the information about S. In method 2, you apply all the qubits, you prepare all the qubits in equal superposition, and you encode this string S with all these single qubit rotation gates, and you apply the static inverse quantum Fourier transformation, and you finally measure all these qubits. So what's new this time is instead of applying the static inverse quantum Fourier, we apply the dynamic inverse quantum Fourier. And in QPE benchmark, it's almost the same. The original benchmark was like this. You prepare all the qubits in equal superposition, you apply controlled unitaries, and you apply the static inverse quantum Fourier. But this time, we have the option of applying dynamic inverse quantum Fourier transform as well. So why dynamic IQFT and not dynamic QFT? If you remember, the loop structure of the gates and the method for our benchmarks, we have the IQFT in the end of the circuit. So since we cannot apply gates after measuring a qubit, having inverse dynamic IQFT is the best option. So it allows us to have some sort of mid-circuit measurement in the overall circuit design. The results were quite interesting. We had 4 different variants for QFT method 1. The first one is with mid-circuit measurement and with dynamic decoupling effect. The second one is with mid-circuit measurement, but without dynamical decoupling. Third one is without mid-circuit measurement, but with dynamical decoupling. And the fourth one is without mid-circuit measurement and without dynamical decoupling. The overall take of the results is that, as you can see in the figure, dynamical circuits with dynamical decoupling effects seems to do better after 6 qubits, is seen in this chart, in this line, that the darkest shade of blue has the highest fidelity, whereas the second darkest shade has like the lowest fidelity. It also demonstrates that the mid-circuit measurement without dynamical decoupling does the worst. What you can see is that the dynamical decoupling effect also enhances the overall fidelity of these quantum circuits. And you would assume that if you add all those dynamical decoupling effect, then it should add the overall execution time, right? But it turns out the DD and MCM effects do not change the overall execution time. Seems like the cost for executing any circuit, any smaller circuit, is around the same, and that is around 1.5 seconds. And that means we can easily get higher fidelities if we just incorporate these mechanisms in our circuits. Overall conclusions: dynamical circuits with dynamical decoupling effects has the best fidelity, at least on IBM phase, and that was the device we ran our experiments. The average execution time are around the same for all of these circuits, and dynamical decoupling improves overall fidelities on all the circuits. Future work: we definitely want to explore more adaptive algorithms. QFT and QP are the basic form of algorithms that allow these mid-circuit mechanisms, but there are definitely more adaptive algorithms and more complex algorithms that we can explore in the future. We also want to replace some of the long connected qubits with MCM and create a hybrid version of these dynamic circuits that has both mid-circuit measurement and these long connected short connected 2-qubit gates. We also want to do more detailed analysis of execution time on larger circuits with more gates. That's pretty much it. Thank you. And now I would like to have Rishikesh to take over the platform.
Thank you, Anish. I'll start sharing my screen now. So, good morning, everyone. I'm Rishikesh. I'm a fifth-year PhD student at NC State University, and I'll be talking about benchmarking quantum reinforcement learning, which is the project I worked during my internship. So, before we even get into what is reinforcement learning or what is quantum reinforcement learning, why should you care about benchmarking quantum reinforcement learning at all? So we found two really compelling cases why you should benchmark QRL. The particular method of QRL which we are using has these distinct circuits, but not all qubits are measured. So you can control the number of measurements on the circuit, and that leads to interesting ways of benchmarking measurement crosstalk and other things. And the second important um, case why you should consider benchmarking QRL is we found that there is a distinct pattern of hybrid quantum classical interactions that can really test the software infrastructure of a quantum HPC setup or any quantum hardware provider setup. And and I will show you later down the road uh, how I can justify all this. Now, uh, like me, not all of us are experts at reinforcement learning. So here is a very quick introduction to reinforcement learning. So reinforcement learning is a subset of machine learning. I'm sure we have all dealt with supervised machine learning like classification, regression, etc. Reinforcement learning is a bit different in that it's a type of machine learning where you have an agent, can be a classical software program or a robotic vacuum cleaner that learns to make decisions by interacting with an environment. So environment can be a game, or it can be a robot that is a robotic vacuum cleaner that is learning to navigate your room. And it interacts with the environment and tries to maximize the cumulative reward. So let's take a simple example where the agent is a robotic vacuum cleaner, the environment is a room, it's trying to navigate the room based on some policy. Policy is nothing but a mathematical or a rule-based function which informs which action to be taken in the environment. And if it runs into obstacle, it will get a negative reward and it will update its policy. And if it takes a good action, it will get a positive reward. Now, what happens? So as the environments get more complicated, the number of actions get more complicated. So you cannot simply use simple mathematical formulas or even a rule-based policy to inform your action. So you need to learn more and more complicated functions. So what has happened within classical reinforcement learning is with the advent of deep learning, you will start using uh, neural networks, artificial neural networks, other machine learning techniques as function approximators to inform your actions. Now, theoretically, you can replace the artificial neural networks as function approximator with quantum circuits. And you can leverage the expressibility of quantum circuits to possibly either to navigate huge observation spaces. And what has been recently shown is that quantum reinforcement learning techniques may require fewer samples from the environment to train or to learn the optimal policy. And there are a plethora of quantum reinforcement learning approaches: quantum Q learning, variational quantum policy gradient, quantum deep Q network. In this particular application-oriented benchmark, we will be using quantum deep Q network to do it. And the problem which we have chosen is a very simple frozen lake problem. In this is a frozen lake environment, which is essentially a game which has 16 discrete states and 4 discrete actions. So your agent starts at the starting square. It can go up, down, left, and right. And purple squares are safe. If the agent steps on a purple square, the game can continue. But if the agent steps on a blue square or it takes an action that makes it go out of the playable area, then the game ends and you have to reset to the starting position. The goal is to reach this green square without stepping out of the game field or on these blue squares. And whatever path that leads to this green square, the game ends and you get a reward of 1. And there is something called as a Bellman equation, which will reward the actions that you have taken to reach the goal, right? So this environment is provided by a third-party library called Gymnasium, and we will be talking on how we interface with that as we approach our architecture. Now, the algorithm which we are using to solve this problem to inform our agent, to train our agent to reach the goal without without stepping on the blue tiles and so on, is something called as deep quantum DQN. So what a deep Q network is, essentially it takes a state as an input and it gives Q values of all possible actions as output. So Q values you can think of as quality values, which is essentially telling how good particular action is given a state, right? So you always choose the action with the highest Q values. And you can see it here in this diagram where you have an artificial neural network. Your observation is your current state. You have encoded it, and the hidden layers are trained weights. And then it will give you the Q value of these 2 actions. And you will choose the action with the highest Q value. Now, instead of these deep neural network, we will be using a parameterized quantum circuit or a parameterized ansatz uh, to give us the Q values. And let's understand how the ansatz look. So, if you remember what we talked about, we need to encode the input state and we need to give Q values of the actions. So you can clearly see that the number of measurements or the number of outputs is directly should be equal to the number of actions you have to take, right? But how many qubits would you require? Well, the number of qubits that I require is generally problem driven. So the number of qubits are either log 2 size of the observation space or the number of actions, whichever is greater. So let's take our 4 by 4 uh, frozen lake as an example. So it's a 4 by 4 grid. So the observation space, all the possible states are 16, right? So log 2 of that is 4. And how many actions we can take? Up, down, left, and right, 4. So total, you need to measure 4 qubits, and you need to have, and to encode the observation space, you need 4 qubits. So you'll have 4 qubits, and all 4 of them are measured. But instead of a 4 by 4, you have an 8 by 8 grid, but with only 4 actions, right? In that case, you will have 64 possible states. So you will require 6 qubits to encode the state, but you will only measure 4 qubits. So you can see not all qubits are measured. Conversely, if you have only a 4 by 4 grid, but 8 different actions you can take, and let's say you can move diagonally as well, then you will require 8 qubits, but you will have to pad zeros in your encoding, and you will measure all 8 qubits, right? And within this ansatz design, we have input scaling parameters. These input scaling parameters are only applied if your binary encoding of your state has 1 in it. So let's say we were to encode 5. Its binary encoding is 101. That's why you see Rx theta 1 and theta 2 is applied. If we were to encode 7, we would have Rx rotations on all. Ry and Rz rotations are nothing but parameters, and this whole structure followed by CZ entanglers, and this structure is repeated. Another distinguished feature of our ansatz is we have this data re-uploading layer, which is essentially uh, uh, the input scaling parameters repeated in each layer, right? And this has been shown to improve performance of QML algorithms. And within our architecture, this is a toggleable parameter. You can choose to have it or not have it. And this is the only parameter within this is the only benchmark between QC app-oriented benchmark that has this. Now, once we put it all together, we'll discuss quickly something about the architecture of this benchmark. So it follows the same modular architecture which Neer mentioned, where you have the API and the kernel libraries inside. The APIs they were written in the language they were written in. The benchmark library is the main entry point for all the functions, and because this benchmark is a hybrid quantum classical benchmark, we have a few other files here. So nvutils, let's say tomorrow you don't want to run a frozen lake, but a different benchmark. So you just have to follow the details outlined, the API structure outlined in nvutils, and you can add a new benchmark, and that's it. You're done. You can run as it is, with a few minor changes, of course, in QRL benchmark. You want to add a new optimizer. Currently, we have support for Atom SPSA. You can add a new optimizer, follow the same structure, and you're done. So that's the entire structure. The user can also provide. The user will provide input. They will be sparsed, and depending on the method, uh, you can either run the entire circuit or run the entire QRL algorithm. So we have methods 1 and 2, as I mentioned before. In method 1, let's say you don't have enough resources to run the entire circuit, run the entire QRL algorithm. You can just run a bunch of circuits. You will get the volumetric plot as well as a creation times and other associated plot within the QED-C framework. This is very similar to our other benchmarks like Hamiltonian simulation, VQE, QAOA, where you have a method 1 and 2, where method 1 just runs the circuit. And method 2, in our case, will run the entire QRL algorithm for a 4 by 4 frozen lake scenario. And the output you will get is plot of circuit evaluations per steps, gradient evaluation, explore and exploit steps, and environmental evaluations. I'll talk more about this in the coming slides. So in method 1, as we discussed, bunch of circuits. You collect the probability distribution from the classical machine, from the quantum device. You do the fidelity calculation and you plot. And we have results for this on a real device, Hyperion Brisbane. We ran from 4 to 12 qubits, and what we saw is up to 8 qubits you can run with high linear fidelity of above 0.75. Uh, Now let's dive into method 2. So method 2 runs the QRL benchmark of frozen lake using DQN algorithm, quantum DQN algorithm end to end. Now, all the orange tiles here are things we have written, and they interface with different parts of the environment. QRL benchmark is your classical part of the uh, classical part, which interfaces with the optimizer and a separate uh, frozen lake environment. And the QRL kernel and the executor form a part of the quantum loop. Uh, all it does is the QRL benchmark informs the QRL kernel to generate the circuit, executes it, processes the probability distribution, selects the action, informs the environment, gets the reward. It also determines whether to explore or exploit. So explore and exploit essentially is whether the action should be randomly sampled in explore, and in exploit, the action should be informed. So only in exploit step, you will be executing a quantum circuit. In explore step, you won't be executing a quantum circuit. You'll just be sampling a random action. And this is done to build uh, a knowledge base of which actions are good and bad, and so that we are not uh, employing the same action again and again and again, right? Um, Now, what you must have noticed is in this previous diagram, there is a classical there is a classical part, a quantum part, right? So you have a parameterized circuit, which we've talked about earlier. You have a hybrid quantum classical loop, and you must be wondering, haven't we seen this before? And it's very natural to ask the question like, how is this benchmark any different from VQE, QAOA, and other QML benchmarks like image processing, which we already have in our application-oriented benchmark? Like, why should we deal with this? Well, the way QRL is different is in terms of this timing characteristics. So the reddish boxes are quantum execution, the blue boxes are classical computer, and purple boxes are it is a classical but a different program. So if you have your standard benchmarks like QFT, QP, where you just do some classical pre-processing, you put it for execution on a quantum device, the results come back, you process, you're done, right? With hybrid algorithms, which require a hybrid quantum classical loop like VQE, QAOA, etc., you do some initial processing, you do quantum execution, parameter update, quantum execution, parameter update. Generally, the parameter updates happen very quickly. Like the resource utilization of your quantum device is very high. So you can book something like a session and you will get your money's worth. Even if your parameter update is very high, your your a hardware provider can figure out a round robin scheduling scheme to maximize the utilization of their quantum resource. But when it comes to highly interactive hybrid benchmarks like QRL, the problem is because you have a third program that is running, and due to the exploit and explore steps being stochastic, which means you're flipping a coin and determining, oh, whether this step is explore or exploit, what happens is you cannot predict when the next execution is quantum or classical, right? So what happens is the quantum device remains unutilized for a long amount of time. So you cannot book a session because it will run too long, or you cannot do a job because it will sit in a queue for long. So this benchmark can really test your infrastructure and motivate something like a priority queue, or like something, or if you're familiar with operating system concepts, if you remember, there is a interactive interactive workloads which require special handling. So that's why this particular benchmark is a bit different from other hybrid algorithms, and it can really test your uh, software software stack. And this is supported by a simulation data. So if you notice this first graph, which is the circuit evaluations per step, so you'll notice initially you have very low circuit evaluations, zero circuit evaluations, and then very sparse, few circuit evaluations, right? And this is all due to initial steps being explore steps. And later, as most steps are exploit steps, once the network has trained, you'll see quantum resources are getting used all the time. Now, now, now to enable better utilization of quantum resources, you would need a very good scheduling trick here. And as you can see, the environmental evaluations are linearly increasing. So if your environmental evaluations are slow, then the gap between this interaction becomes even longer. So that's why it's a bit different. So in conclusion, QRL can prove an effective benchmark in characterizing a QC's ability to handle different hybrid classical workloads. A QRL ansatz with variable number of qubits, uh, because you can measure different number of qubits, it offers a distinct circuit to be benchmarked. We cannot really control the number of qubits measured in any other benchmark within the application-oriented benchmark we have. So somebody who is, let's say, benchmarking for measurement crosstalk can use this ansatz to change the number of things that are measured and get that data. And we also have a toggleable data re-upload layer within the ansatz. So and because this is the only ansatz that has this, the current benchmark, you can use it to test the data re-uploading technique, the efficacy of data re-uploading technique. Uh, and in future work, we are adding a new metric called sample complexity, and this will be added very soon. That's a current work in progress. We are also working on a more complicated ansatz design and more different optimizers apart from ADAM and SPSC, which are currently supported. And we are also thinking of exploring other QRL algorithms like actor-critic, reinforce, and bunch of others. With this, I would like to conclude and thank all my collaborators, Neer, Anish, and my mentors, Tom, Sivan, and also John for their support. Thank you.